In the last video, we learned that the Gibbs approach, along with some sort of assumption that we are able to actually get to equilibrium, allowed us to derive the entropy for a simple sort of example case, the ideal paramagnet. In this video, we're finally going to look at the ideal gas. And this is also the video where I want to name the assumption that we're at a uniform probability density function over some space. And the name that this is given, which I find a little bit upsetting, honestly, is the Microcanonical Ensemble. The reason I find this somewhat upsetting is that the idea that we need ensembles is actually a little bit problematic. So the Gibbs approach works even if we think that probability comes from some other place. So for instance, one place probability could come from is our lack of knowledge about the system, epistemic uncertainty, effectively. Um, the statement that we need ensembles, that is to say, we need to prepare many, many different systems in different states, seems to not work very well because that's never what we do in the lab. But I digress. What it's called is the microcanonical ensemble, and in this lecture, we're going to see why we might want to think about it as in some way micro, or having to do with something about micro states of the system. And that's because in this video, we're going to look finally at the ideal gas. So let's keep in the back of our minds and on the board that what we're trying to do is derive the entropy for the ideal gas, the Sackur-Tetroda equation that we've been using all for the entire course. Now, I'm going to start right away with the particle in a box. And let's start in just 1D. So those of you who have taken quantum mechanics before will know what the solution is here. There are a variety of energy levels in the particle in the box, and we can look at what their wave functions look like in one dimension. The real form of the energy eigenfunctions look like standing waves. So we get one like this, we get one like this, we get one with 3 nodes. And as we increase the number of nodes from 1 to 2 to 3, we're increasing the energy. In particular, the energy levels are, well, I should say maybe the nth, or the nth energy level has the value h bar squared pi squared over 2ml squared, all times n squared. So they go like n squared. Good. Okay. So this is just for a one-dimensional particle in a box, but it turns out that generalizing to more dimensions is relatively easy. So if we're in d dimensions, then rather than the states being indexed by a single number n, they'll be indexed by 1n for every dimension. So we'll have energy levels that look like, or that are indexed by n1 through nd. Great. And the value here, well, it'll be the same prefactor, h bar squared pi squared over 2ml squared. But then we'll multiply by n1 squared plus n2 squared plus dot 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 plus nd squared. Excellent. Now, if in addition to working in d dimensions, we also have many particles, and we want to think about what the energy eigenstates should be there, let's assume that those particles don't interact with each other. If they aren't interacting, then their energies just add. They just sort of exist in the same space, and we consider the total energy of the system to be the sum of the energies of all the particles. So if n particles in d dimensions, then it's just the exact same situation, but now rather than going to d, we'll go to n times d. So we'll get en1 through n nd, same prefactor, h bar squared pi squared over 2ml squared times n1 squared plus dot 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 plus n nd squared. Excellent. Okay, so There we go. That's something to start with. But now we actually need to figure out the number. Remember that what we're looking for is the number of states with a given energy. Now, immediately, this becomes really challenging. Let's imagine that we only have two of these indices n in the first place. Then we're looking at all of the lattice points in two dimensions. So say this is n2, this is n1. And so these are just all of the sets of two integers. And I should point out, sorry, these integers need to be positive. So here we need n is a positive integer. So is an element maybe of z greater than, strictly greater than 0. And so here, all of these need to be strictly greater than 0. So let me amend my diagram a little bit by just erasing these parts of it. Good. And so on. Okay, so if we want all of the solutions for the energy, those will actually be all the lattice points that land on on a certain circle with a certain radius. Why is that? Well, it's because of the functional form that we have here. We're adding the squares of these ends. So we're interested in all, if we're solving for a given E, in all the lattice points that are a certain distance away from the origin. So let me draw that in. We would look at a certain distance from the origin and see how many lattice points hit this. Now, answering that exact question is somewhat challenging, counting the number of tuples of positive integers that are a fixed distance from the origin. Hard combinatorics problem. And so we're actually not going to solve it at all. And you'll see why we can do that in a second. The first thing that we need to do is look at generalizing this to more dimensions. So I want to think about the same picture, but in a large number of dimensions. Now, I'm going to rely on a fact. This fact sometimes gets associated with Carl Friedrich Gauss and would be called Gauss's circle problem, or the solution to Gauss's circle problem, which is how many integer lattice points are inside of a circle of a certain radius. Okay, so it's not clear that that has anything to do a priori with the question of how many lattice points are on the circle itself, but maybe it's not hard to see that they will be related. Let's just get there in a second. So the number of lattice points, integer lattice points, inside a circle of radius r is approximately the area of the circle. Okay, and this generalizes in a couple of ways that are important for us. The first is that by symmetry, the number of lattice points inside of the quarter circle is just 1/4 of the area of the circle, or it's the area of this quarter circle. Good. The second thing is that it generalizes to more dimensions. So the number of integer lattice points inside of an n, or a hypersphere in n dimensions, is going to be approximately the hypervolume in n dimensions of that hypersphere. Good. So if we are thinking about, sorry, capital N particles in 3 dimensions specifically, then we're interested in looking at the 3n dimensional hypersphere. But we don't want the entire hypersphere. We just want the part where every index is positive, which means we want 1 over 2 to the 3n of the hypersphere. So this implies the number of lattice points inside a hypersphere in 3n dimensions of radius r is approximately, well, 1 over, oh, sorry, is approximately this number here. Let's maybe give that a name. We'll say this is V. So the number of lattice points in the let me say the positive part of this hypersphere is Vn times 1 over 2 to the 3n. Good. Okay, but how does this help us at all? Well, let's just talk through it. Suppose we could find this number of lattice points in this positive part of the hypersphere. Then we push that volume or the radius out just a little bit. Then we know that in that small bit that we've increased is the remaining points that we've added. So if we look at the number for radius r, and then the number for radius r plus delta r, and delta r is small, then we know that all of the rest of those numbers are in that thin shell. And that's probably as good as we're going to do. So if we can figure out how many are in a thin shell right around this radius, then we're golden. I'm going to erase the board and we'll make that a little bit more formal on the next one. Okay, on the last board, we talked through how we could turn our problem of finding the number of solutions to n1 through nd such that this quantity was equal to a fixed value of E. How we could relate that to a problem of geometry, of finding the volume inside of some ball, and then using that to find the number of states inside of a little spherical shell. Now, on this board, I want to actually make that a little bit more formal and be careful with the math. So, if I set this to a fixed value U, so suppose that I want to look for solutions around energy U, well then I'm looking for n's with a particular radius in n space. To do that, I need to think of, okay, so I have my n1 squared plus dot 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 plus nnd squared, and that should be equal to r squared. So I need to multiply everything else over. So I get my n1 squared plus dot 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 plus nd squared is equal to 2ml squared u over h bar squared pi squared. And that is equal to r squared, which implies that r is equal to the square root of 2mu times L all over h bar pi. Good. Okay, so now that we have R and we know that our number, sorry, that our our number of lattice points in the positive part of the hypersphere. Well, we said that that was 1 over 2 to the 3n times Vn. So let's write that is 1 over 2 to the 3n times pi to the d now is going to be replaced with 3n over 2. We'll leave r for a second, over gamma of n over 2 plus 1, but I'm actually just going to rewrite that using a factorial, even if this factorial isn't an integer. We'll just remember that it really means the gamma function. Okay, so I would just take the 1 away, and this would be n over 2 factorial. But that's 3, oh, and that n should be a d, my mistake. And this should be vd as well. All right, anyway, so this should be 3n over 2 factorial. Excellent. Okay, so then times r to the 3n. So what will that give us? L to the 3n over h bar to the 3n pi to the 3n. Then 2mu is raised to the 1/2, so this will be 2mu to the 3n over 2. Wonderful. Okay, now I'm going to say that the number of states in here, by some abusive notation, I'm going to call omega of u. In the past, I've used this for the exact number of states at a particular energy level, but you'll just have to remember that it means something a little bit different here. Okay, so now let's reduce this just using sort of normal algebra. So notice this 3n over 2 is going to partially cancel this down to pi to the 3n over 2. L to the 3n, I'm going to rewrite because we're going to say that this is just a box. So if all of the L's are the same for the 3 dimensions, then L cubed is V. So I'm going to rewrite this as V to the n. Great. Then lastly, I have 2 to the 3n in the denominator and 2 to the 3n over 2 in the numerator. So this will cancel down to a 2 to the 3n over 2. Great. All right, so when all is said and done, I now get omega u is equal to 1 over, let me put the 3n over 2 factorial first. Then I'm going to get v to the n, sorry, m to the 3n over 2, u to the 3n over 2, over 2 to the 3n over 2, h bar to the 3n, pi to the 3n over 2. Excellent. All right, so now if I were to increase u by a small amount, so if I were to look at the number for u plus delta u, all that would mean is plugging delta u in here. And I want to look at that minus u, omega of u, which would be the number if I just look in my sphere. So let me just show what I'm doing here in my two-dimensional example. So omega u would be like the number in here. But we actually just want the number in this little shell right here. So what we're doing is taking the whole number inside of the bigger shell and then subtracting the number in the littler shell. Good. But look at this. This looks almost exactly like a first derivative. So all I need to do is say that this is equal to omega prime of u times delta u, roughly speaking, and maybe just to be clear, this is only approximately true. All right, so this is the quantity that we want. So let me put a star right here. We want to calculate that. This is going to be the number that is approximately the number of solutions to that equation. Good. All right, so if I were to take this derivative with respect to u, that would just mean bringing down a 3n over 2, and then I get a 3n over 2 minus 1. Okay, the 3n over 2 would actually cancel one term in this factorial, and then I'd have to multiply by delta u. Now, oftentimes, this object here, this derivative of the number of states inside an energy u, is called g of u, and that is given the term density of states. It's a density because it's like the number of states per energy. Good. That's just something to point out. It's not going to be important to the rest of the derivation. All right, so now what do? We just write this down. So our star is going to be equal to 1 over 3n over 2 minus 1 factorial. And then all this stuff gets copied down just as it was. So v to the n, m to the 3n over 2. But u loses a power, which went to canceling something in there. So this becomes 3n over 2 minus 1. Remember, we need to multiply by delta u. Then divide by 2 to the 3n over 2, h bar to the 3n, pi to the 3n over 2. Great. So this is our number of solutions to that original equation, this one here. And it's rough, right? Because we're looking really at this whole shell, not just at an infinitely thin circle. But it will turn out that when we take the log, this won't matter very much because the width of the shell will actually not be important to the final solution. And that means we can take that width to be as small as we want. So we're going to consider this good enough. So now we're ready to find S. And I'm going to combine the steps, actually, of finding S and doing Stirling's approximation. Okay, so now we're ready to find S, which is just going to be kb times the log of this object, which is the number of states that we're looking for. Okay, so without further ado, S is equal to, and let me actually call this S naught for reasons you'll see in a second. S naught is equal to, well, let's make this approximate actually, because I'm going to do Stirling's approximation in here. First of all, we get a whole bunch of quantities which are not going to depend very strongly on anything that we care about. So let me go ahead and circle those. So recall that N, V, and U, or UVN, are our internal energy work coordinates in thermodynamics. So we care very strongly about those. All the rest of these have N in their exponents, but otherwise don't depend on N. So let's pull those out first. When we take the log, we're going to get these powers coming down. And notice that other than h bar, these are all raised to the 3n over 2. Okay, so let's divide by kb just to make our lives a little bit easier. And then we can say that this is 3n over 2 times the log of m over 2 pi h bar squared. Great. Now the units may not all work out here, and we're going to have to fix that in a second. Next, let's deal with this v term. So that's going to give us n log v. Good. Next, we can deal with u. And I forgot my delta u here. So actually, I'm going to go ahead and ignore this right away. And why? Well, if I take something, all this stuff to the n, and n is huge. I mean, the number of particles in a box of gas, right? Could be 10 to a big number. And then I look at this width that I'm taking to 0, that's going to be relatively small. So I'm going to go ahead and say that we can ignore that. Great. Okay, so let's go back to it. We have n log v, then plus 3n over 2 minus 1 log of u. But notice again that if 3n is really, really large, then that minus 1 doesn't affect things very much. Excellent. Okay. Next up, we have this term here. So that's going to give us a, by Stirling's approximation, minus 3n over 2. Notice I'm going to neglect the minus 1 again just because it's relatively small. Log 3n over 2. And then plus 3n over 2. Good. Okay, but why did I call this S naught? Well, the answer is that there's a fundamental quantum mechanical phenomenon, which is indistinguishability versus distinguishability of particles. So some particles in quantum mechanics are distinguishable from each other, and some are indistinguishable. And notice that when particles are indistinguishable, what happens is that the Hilbert space of possible states for those particles shrinks. In other words, there is no physical way to tell apart particle 1 being in one state and particle 2 being in the second state from the situation where those two particles' identities are switched. So particle 2 is in the state that particle 1 was in the last example, and particle 1 is in the state that particle 2 was in. Because of that, we're actually overcounting the number of states here, right? Because I've assigned particle 1 to be in one state. So for instance, if I look at this picture here, I've assigned particle 1 to be in this state and particle 2 to be in this state. But that overcounts things. I need to reduce by some factor the number of states that I've counted. But what is that factor? Well, if I have n slots and n particles to put in those slots, then I need to think about the fact that I could put n particles in slot 1. Okay. But then once I've filled slot 1, I have n minus 1 particles left to choose from. So I can put one of n minus 1 particles in slot 2, and then one of n minus 2 particles in slot 3. This means in the end, I get n factorial different choices for different ways I could arrange these particles into the states that I've picked. So to find the real S, we need to introduce an indistinguishability factor. So what we need to do is think about taking this star equation and multiply by 1 over n factorial for indistinguishability. If we do that, then we get another minus n log n plus n over here. And let's notice what this gives us all in the end. Okay, so I'm going to start underlining factors that share some things in common. So all of the terms that have logs in them, let's underline here. Good. And then we have these two terms that don't have logs. All right. So if I take the terms that do have logs in them, and I push everything but n inside of the log, so I start raising the argument of the log to various powers, I'll get the following after I make combinations. N times a log. Now from here, I'm going to get m over 2 pi h bar squared to the 3 halves. Okay. Then here I just get v. Here I'm going to get u to the 3 halves. Down here, I'll get 3 halves n to the 3 halves in the denominator because this is attached to a minus sign. And then here I'm going to get just n by itself. And then for the non-log terms that I've underlined in green, I get net plus 5 halves n. And you may be noticing something very interesting happening. Now I'm going to transport this equation to the top of the next board, and I'll see you in a second. Now here's where we left off on the last board. And you'll notice that we're getting awfully close to the Sackur-Tetroda equation. The only thing that's off here is that this term needs to all be combined into sigma. So we have the requisite v to the 1, u to the 3 halves, and n to the net 5 halves in the denominator. We just need to rearrange everything else. So what that means here is just going to be moving this 3 halves from this term into this term. But notice that all of this stuff was also raised to the 3 halves. So we're actually okay. This is just going to become a 3. Good. And this gives us our first glimpse into what sigma really came from. So sigma came from properties of the particle, namely the mass, and of quantum mechanics in general, namely h bar. Remember that sigma was actually observable when we got to a chemical joint. So when we started trying to mix 2 boxes of gas with each other, we actually were able to get observations of sigma itself. And that means that there is actually a way that we can see that kind of quantum effect even in thermodynamics, which is pretty cool. Now, the real upshot of looking at the ideal gas here, and the fact that we can get the ideal gas law, which we've used forever, just from statistical mechanics, is that now we should have much more confidence that we've stumbled upon something correct here. It could have been that for the example we did in the last video, the ideal paramagnet, the system is just so simple that even this kind of sketchy math approach that we've taken is going to get us the right answer. But I feel like the ideal gas has enough going on that we should have some confidence now that statistical mechanics can give us some real intuition, or at least, some real answers about what the entropies should be in classical thermodynamics. Okay, one last thing. The microcanonical ensemble idea. I said that I would talk about this, and I think it's time to do so. The idea of the microcanonical ensemble is that we're trying to count so-called microstates. Now, I mentioned that the Gibbs approach doesn't really need microstates to work, but it does help us a lot when we're in the quantum case, in which we really do, by our assumption, have discrete eigenstates, eigenvalues, I should say, for the Hamiltonian. So here, what we're really trying to do, again, is count some number of lattice points which intersect a circle. In other words, we're trying to do some counting problem involving microstates. And so this gains the name the microcanonical ensemble. But it doesn't mean that thermodynamics gets information about those microstates. They're counted, aggregated, and then forgotten about. So this is another place where I feel like the terminology is a little bit unfortunate. In any event, in the next video, we're going to do one more example in the microcanonical ensemble before we move on to some really exciting new physics. I'll see you then.